Hey guys, so today we're going to be covering material from Chapter 9 for the Math 200 class. We're going to be talking about estimating the value of a parameter. So we're going to start with section 9.1, which talks about estimating a population proportion, and then we're going to move on to 9.2, which is about estimating a population mean. So we're going to go through kind of a lot of definitions today to just kind of get you guys acclimated with what a confidence interval is, and we'll also throw some definitions in, or some examples in there so you can see how these are actually constructed. So first definition is actually a review from the previous chapter. So a point estimate is the value of a statistic that estimates the value of some parameter. So for example, the point estimate for the population proportion is denoted with a p with a little hat on top. We just say it as p hat. And what we do to find that is we just take x over n, where x is the number of individuals in the sample with some specified characteristic, whatever we're interested in basically, and n is just the sample size. So let's look at this example here. We have a July 2008 university poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. And 1,123 out of the 1,783 were in favor. So first thing we want to just do is we want to obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. And in order to find that, all we do is we're calculating p hat by taking what we're interested in, which is basically people who are in favor of the death penalty, so 1,123 people out of our total 1,783. And we get a p hat value of 0.63, or you could think about this as about 63%. So that back here, this is just same stuff from chapter 8, where we're just finding our population, or we're finding our sample proportion. Now, what we want to actually be able to do with this is we want to take this sample and we want to be able to apply it to the whole population. So we know that probably if we asked everyone in the entire United States this question, the actual population proportion wouldn't be exactly 0.63 or 63%. It would probably be pretty close, but it wouldn't be exact. So what we do is we create something called confidence intervals, which is basically just allows us to give two values, and we can give a different level of confidence. So basically we can say we're 90 or 95 or 99% confident that the true population proportion lies between, and then we just list the two values. So that's what we're going to be doing now, is we're going to be taking our p hat value and we're going to be using it to help us construct a confidence interval around which we think the true population proportion, or in which the true population proportion hopefully would lie. So a confidence interval for an unknown parameter consists of an interval of numbers based on some point estimate, and the point estimate is the value of p hat that we just talked about. Now, we also always have a level of confidence associated with confidence intervals, and basically this just represents the expected proportion of intervals that are going to contain the parameter if a large number of different samples is obtained. And this is typically denoted as 1 minus alpha. Okay, you're going to want to get used to seeing this Greek letter alpha times 100%. Okay, so alpha is basically what we will later refer to as our type 1 error, but it's kind of basically the probability of making an incorrect conclusion. So our level of confidence would be how confident we are, and alpha is kind of how not confident we are. So for example, a 95% level of confidence would go with alpha equals 0.05, which corresponds to 5%. So for 95% confident, we're basically 5% not confident. And what this implies is that if we took 100 different confidence intervals and we constructed them, each based on a different sample from the same population, we would expect about 95 of those intervals to actually contain the parameter, and then the other 5 would not contain the parameter. That's what 95% level of confidence means. If we had 90% level of confidence, it means that we would only expect 90 out of the intervals to contain the parameter, and then 10 of them wouldn't. If we wanted 99% confidence, that would mean that 99 out of 100 would contain the parameter and only one would not. Now, in order to construct a confidence interval, it's always kind of the same form, but we have different actual formulas based on what we're dealing with. So what we do is essentially we take the point estimate, which is either our p hat or our x bar if we're talking about a mean, and we add and subtract what we refer to as the margin of error. Now, the margin of error of a confidence interval estimate of a parameter is just a measure of how accurate the point estimate is, okay? So it involves a couple of things. It involves basically three different things. It involves the level of confidence. So as we want higher and higher confidence, our margin of error is going to increase, okay? So if we want to be very, very confident, we're going to have a large margin of error in order to kind of make up for that. Now, as our sample size increases, the margin of error actually decreases, which makes sense. As we are allowed to take a larger and larger sample, we would expect our error to go down. And then the third factor for margin of error is the standard deviation. So the more spread that there is in the population, meaning the higher that the standard deviation is, the wider our interval will be for that given level of confidence. So let's kind of remind ourselves about the sampling distribution of p hat. This is from chapter 8. So for a simple random sample of size n, the sampling distribution of p hat is approximately normal with a mean mu of p hat equal to p and a standard deviation, which we called the standard error. And that's just found by taking the square root of p times 1 minus p over n. And this can all be done provided that two things are true. N times p times 1 minus p has to at least be 10. And then it's also required that the trials be independent, meaning that if we're dealing with some finite population, which typically are like people in the US or something like that, we're taking a sample that is smaller than 5% of the population size. So we have our formulas here, which allow us to construct a confidence interval for a population proportion. And what you'll see here is that we have a lower bound and an upper bound. So whenever we're giving a confidence interval, it's always going to be between two values, a lower and an upper bound. Now, they look absolutely identical except for these signs right here. For the lower bound, we take p hat and we subtract z alpha over 2, which we'll talk about in a minute. This is called your critical value, multiplied by square root of p hat times 1 minus p hat over n. And then for the upper bound, you do the exact same thing, but instead of subtracting the margin of error here, you add the margin of error. Now, again, to kind of just reiterate this, it has to be true that n times p hat times 1 minus p hat has to at least be 10, and your sample size has to be less than 5% of your population size in order to be able to actually construct this interval. So I kind of mentioned back here this z alpha over 2, this right here. This is called your critical value. So we're going to talk about critical values a lot, but you'll see that you have to find a critical value for every confidence interval you create by hand. So confidence intervals can be really of any level, but typically we're doing one of three confidence intervals, either 90, 95, or 99%. Those are the three most typical. Now, this is a nice little table that gives you basically the levels of confidence and the critical values that go with it. These are probably numbers that will just eventually stick in your brain because you'll see them so many times, but I wanted to also put them here so we can see that these are kind of the three values that we'll most often be referencing for population proportions. So if you think about it, if you have 90% as your level of confidence, basically what that means is that we have kind of a 10% error that we're dealing with, okay? 10% is our alpha value. So if you think about that in terms of your nice little bell curve, you're going to have your 90% hanging out in the middle, and you're going to have 5% in each of the tails. So the way that you want to think about it is that you have 5% on the left-hand side, 5% on the right-hand side. And what this corresponds with is actually a z-value from the normal distribution table of 1.645. So if you actually go to your table and you look for, in the body of the table, you look for the value closest to 0.05, you're going to find 1.64 and 1.65, and this is smack dab in the middle between those. Now, if you look for 95% confidence, that means that we have 5% kind of not confident, okay, which would mean that we have 2.5% in each tail. So again, if you go to your z-table and you look in the body and you try to find 0.025, the closest value you should find should be the 1.96, and that's your critical value there. 99%, that means that we're kind of 1% not confident. So in each tail, we would only have 0.5%, which corresponds to 0.005. So if you look for that in your table, again, this is kind of like the first one. It's not an exact value, but it's going to be somewhere close to 2.57 and 2.58. It's pretty much smack dab between those two at 2.575. Now, in order to interpret a confidence interval, we have kind of a standard way of writing these, but what we can say is that a blank percent confidence interval, so if you're doing a 90%, you would put the word 90 here. So a blank percent confidence interval indicates that blank percent, so that same percentage, so a 90% confidence interval indicates that 90% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. So basically what that means is that if it's a 90% confidence interval, 90 times out of 100, we're going to end up with a confidence interval where the parameter is actually contained in that interval, and only 10 would result in something where the parameter is not contained in that interval. So let's look at an example where we calculate this by hand, and after we do it by hand, I'm also going to pop open StatCrunch so you guys can take a look at that. So we have the same poll with our 1,783 registered voters. 1,123 of them said that they were in favor of the death penalty. And what we would like to do is we would like to go ahead and obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So what we're going to do first is you're going to find p hat, which we've already found. That's just found by taking x, which is what we're interested in, over n. So we took our 1,123 and divided it by our 1,783, and we get 0.63. Now, it would also be a good idea to make sure that our conditions are met. So in this case, we're going to take our 1,783, which is our sample size. We're going to multiply by p hat, which was 0.63, times 1 minus p hat. And when you multiply all of those, you get like 415.6, which is obviously much larger than 10, so that condition is met. And the sample size is only 1,783. That's definitely less than 5% of your population size, because your population is going to be any registered voter in the United States, so it's a very large population. Now, in this particular case, they asked us to create a 90% confidence interval. So that would mean that our kind of not confidence part is the 10%. So we know that alpha is going to equal 0.10. Now, if we go back a couple of slides, we can see that 90% goes with a critical value of 1.645. So that's going to be our critical value here. So in order to create our confidence interval, I'm going to just go through the lower bound because the upper bound is the same thing except with a plus sign. So we take our p hat, which is our 0.63, and then we subtract our critical value, which was our 1.645. And again, it's typically going to be one of these three values here. And you take that 1.645 and you multiply that by the square root of p hat, which was 0.63, times 1 minus p hat, 1 minus 0.63, over n, which was 1783. Now you need to be very, very careful putting this in your calculator. My suggestion would be to pause the video for a minute, try it in your calculator, make sure you're able to get these answers. If you're having any issues, make sure that when you type this in, you go ahead and put an extra set of parentheses right after you hit the square root key, and don't end that set of parentheses until after the 1783. But other than that, you should be able to kind of just put it in exactly like you see it here. You should end up with a lower bound of 0.61 and an upper bound of 0.65. One thing you'll notice is that since we're just adding and subtracting the same value, basically your p hat, your estimate for your population proportion, is going to be right in the middle between the lower bound and the upper bound. So if you think about it, 0.63 is smack dab in the middle between 0.61 and 0.65. This should always be the case. This is a really good kind of easy check to make because all you're doing is you're adding and subtracting the same value. So you should end up with this original value, your p hat value, right in the middle. So if we wanted to interpret this, we could say that we are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is somewhere between 0.61 and 0.65. Now you could replace the word proportion and put percentages here. Okay, so you could say we are 90% confident that the percent of registered voters who are in favor of the death penalty is between 61% and 65%. That would be fine as well. Either way is okay. And this is kind of an interpretation that you'll want to get used to. These start to all kind of look the same, and that's okay. We can sort of always use the same little template. Basically, we can say we are, and then we put the confidence level, and then we have to put a little context around it. So in this case, we were talking about registered voters who are in favor of the death penalty. This could vary based on the question. We could be talking about, for example, the proportion of Americans who approve of President Obama, okay, something like that. And then we just give the two values that we calculated. Now, this is, it's pretty easy to create the confidence intervals using StatCrunch. So I'm just going to minimize this real quick, and I have StatCrunch open. I'm going to show you guys how to do this. So let me move my screen over a little bit. So if we look here, what we're going to be doing is stat, proportion stats, and then we have, we have one sample, and I'm going to have to move this over a little bit. We have one sample. Now, if we had a bunch of data, like if we had one row for every person who is surveyed and it said either in favor or not in favor, then we would do with data. But our data is already summarized. We have the total number of people who were asked the question, the total number of people who responded in favor. So we're just going to do with summary here. And then all we need to do is just put in the information. So I have 1,123 successes because we're considering someone who is in favor of the death penalty to be a success. And then we have a total of 1,783 total observations. And then you'll notice here there's this little kind of radio button. Hypothesis test is the default. We're doing those in the next chapter. Right now we're doing confidence intervals. So you want to make sure you go ahead and select that. And the level that we want is 90%. So we put in 0.90. You can just leave this method alone. And then you're going to click compute. And if we look here, let me move this over. You'll see it gives you a bunch of information. It calculates your sample proportion for you, that 0.63 that we got. Also calculates the standard error. And then it gives us a lower limit and an upper limit. So if we look back at what we had for our answer before, we had 0.61 and 0.65. We have the same things. These are a little more exact. They haven't rounded as much as we did. But we get the exact same limits. All right, let me maximize this again. There's one kind of other type of question that we can ask in this section. So the first and the most important is the confidence intervals. But we can also use the same kind of information to do sample size calculations. So let's say, for example, that we want to obtain a sample and we know what level of confidence we want, we know what type of error we are willing to deal with, but what we don't know is how many people we should sample in order to kind of guarantee that we end up with the desired level of confidence and the desired margin of error. So what we can do is kind of one of two things. So if we already have a prior estimate, meaning that someone has already conducted a sample and we know approximately what our proportion is going to be, we can use this first formula here. Okay, so this can be used anytime you have a prior estimate. Now, if you don't have a prior estimate, so no one has ever studied what you're interested in, or you simply don't trust the prior estimates at all, what you can actually do is you can just use this formula here, which is pretty basic. Basically, all you're going to do is replace p hat times 1 minus p hat from the first formula with 0.25. And if you don't use prior estimates, you're going to end up needing a larger sample size to get the desired margin of error and level of confidence. If you have a prior estimate and you trust that prior estimate, then you're able to take a slightly smaller sample size in order to meet those same requirements for the level of confidence and the margin of error. So let's take a look at this example here. So a sociologist wanted to determine the percentage of residents in America that only speak English at home. And what we want to know is what sample size should be obtained if the sociologist wants her estimate to be within 3 percentage points with 90% confidence. And she's going to use the 2000 estimate obtained from the census. It was from a supplementary survey. And that proportion was 82.4%. So she's using a prior estimate. So it's important to kind of outline all of the information that you need here. But if you take a look back at our formula, since we're using a prior estimate, we need our p hat, which is our prior estimate. We need z alpha over 2, which is our critical value, and we need e, which is our margin of error. So if we take a look here, she wants the estimate to be within 3 percentage points. So that means that the margin of error, our e, is 0.03. Now, she also says that we want 90% confidence. Now, 90% confidence, if you remember from that little table we've looked at a couple times now, the critical value that goes with 90% confidence is 1.645. So that's going to be our critical value here. Now, our p hat is just the 82.4%. We want to write it as a decimal though. So that was the prior estimate from that 2000 census supplementary survey. So we write it as 0.824. And then all we have to do is just find our sample size. So we take our p hat, which was our 0.824, times 1 minus the p hat, which is 0.824, and we multiply that by 1.645, which is our critical value, over the margin of error. This little piece right here is squared, okay? So you're going to want to make sure you plug this into your calculator very carefully. You should be able to plug it in pretty much exactly how it looks right here, and you should be able to get the answer. And I would go ahead and pause the video. You should be able to get an answer of 436.04. So go ahead and pause it until you're able to get that. Now, if you think about it, we're calculating sample size. So we're talking about number of people. So we cannot have 0.04 part of a person, okay? So anytime you're doing a sample size calculation, no matter what comes after the decimal, you always have to round up. Because if I only actually sampled 436 total people, I would not quite meet the requirements that I'm wanting for my margin of error and my level of confidence. So what I have to always do with sample size calculations, always, is round up. So this means that the sociologist has to ask 437 randomly selected American residents this question in order to have the desired margin of error and desired level of confidence. Now, we can also use StatCrunch to do this. Now, just a word of warning, this is kind of a new addition to StatCrunch since I taught the class last time. So just be kind of careful when you're using it. Make sure that my math lab likes the answers. You can always let me know if for some reason it doesn't. It should work. I was able to replicate the answers pretty closely in StatCrunch, but just be careful of this because I have not used this functionality before. That's why it's not included in that StatCrunch user guide. But let's take a look at this one, and let me kind of bring StatCrunch up. We can use it to go ahead and get our answer here. So you start the same way as the confidence intervals, which is just stat, proportion stats, and then one sample. But this time we want a power or a sample size calculation, so we go ahead and click on that, and this looks a little different. Now, we don't want hypothesis test power, we might use this later. Right now what we want is confidence interval width. And this is actually pretty cool. It's like a little slider bar that you can kind of just mess with, and it will tell you different sample sizes and the widths that go with those. So what we need to do is just enter the information we have. So our confidence level was 90%, so we should enter 0.90. And our target proportion, that's our p-hat that we have right now, which is 0.824. Now, the thing that's a little tricky that you have to kind of remember is that margin of error is added and subtracted from your proportion. So the margin of error that we are willing to deal with is 3%. Now that's in either direction. So if you're entering the width of the confidence interval, you actually have to multiply that error by 2. So in this case, the 0.03 actually becomes 0.06. And now if I click compute, I get 436 people. Now you'll notice that my width was changed. Okay, so they put exact values here. I typed 0.06. This width is 0.059999761. They got a sample size of 436. Their calculations are going to be slightly more exact than ours because they have slightly more exact critical values. So hopefully my math lab is able to deal with these answers without any issues, but you can always let me know if you do have any trouble. But this is how we do our sample size calculation in StatCrunch. Okay, now let's take a look at section 9.2. So this is about estimating a population mean. So 9.1 was all about population proportions. 9.2 is all about population means. Now, you'll know from chapter 8 what the difference between those two things are, and we have some different kind of formulas that we're going to have to use based on if we have a population proportion or a mean. Now, again, some definitions here. I'm going to introduce you guys to a new distribution in this section. So we've dealt with normal distribution, binomial distribution. Now we're going to have something called t-distribution. But you should already be familiar with this definition here. A point estimate we know is the value of a statistic that is used to estimate the value of a parameter. So the sample mean, x bar, is a point estimation of the population mean. And we have seen this before, okay? I think we've walked through this same example before. We have pennies that are minted after 1982. We have, I think there are 17 different penny weights here. And if we treat this data as a simple random sample, if we want to estimate the population mean weight for pennies minted after 1982, all we would do is just add up all of our observations and divide by 17, which is our total number. So all we're doing is we're finding the average. So we have x bar, which is our sample mean, equaling 2.464. So that would be the point estimate of mu that we would use. Now, I want to talk about students' t-distribution because instead of using the normal distribution, we are using students' t-distribution now. So let's suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, then the distribution of t, which is calculated by taking x bar minus mu divided by s over square root of n, is going to follow the student's t-distribution with n minus 1 degrees of freedom, and x bar is your sample mean, and s is the sample standard deviation. Now, you'll notice there's no sigma in this formula, and that's why we're using student's t-distribution, actually. So with the normal distribution, we have to have a population standard deviation. Now, typically, we don't actually know what that is. When we have a population proportion, we're able to calculate it. But when we just have a mean, okay, so let's say we're talking about average income or something like that, we have no idea what the population standard deviation for that parameter is. So what we use is we use students' t-distribution, which gives us a very nice, basically, relation that allows us to use the sample standard deviation instead of the population standard deviation. Now, there are a lot of properties of our students' t-distribution. You don't need to sit down and memorize all of these, but you should be familiar with them. So, we're going to talk about degrees of freedom. That's related to sample size, and the t-distribution is different for all different degrees of freedom. Now, it's centered at 0, symmetric around 0. Area under the curve is 1. Area to the right of 0, area to the left of 0 are both 1/2. As t increases or decreases without bound, the graph approaches but never equals 0. So a lot of these things should sound very familiar. They're pretty much the same as the normal distribution so far. Now, this fifth one, the area and the tails of the t-distribution are a little bit greater than the area that are in the tails of the standard normal distribution. So since we're using S as an estimate of sigma, we're introducing a little bit more variability into our t statistics. So this is just kind of one of the things that happens because of that. Now, as our sample size increases, the density curve of t gets closer and closer to the standard normal density curve. This result occurs because of the law of large numbers, which we've talked about before. So as sample size increases, S gets closer and closer to sigma, and that is due to the fact that we have this law of large numbers, which tells us this. So if we take a look at on kind of a little graphic what this looks like, the blue is just your normal distribution. You'll see it has the smallest tails, okay? But it looks very, very similar to these others. The pink, which it's kind of hard to even tell the difference, but the pink one is just slightly higher in the tails. This is for n equals 15. And the orange, which is for n equals 5, so these are your sample sizes. This looks very similar as well, except it has a little bit higher of tails. So as you have a larger and larger sample size, you see it starts to get closer and closer to this blue. So if we looked at this for n equals 50, n equals 100, it would be even closer to the standard normal. Now, the notation T alpha is just the t value such that the area under the normal curve to the right is alpha. And if you look at this notation here, this looks a little bit different than when we were talking about normal distribution. Normal distribution gives us area to the left, but for this one, the area alpha is just the area to the right. So if this is your t-distribution, this would be t alpha. So let's take a look at how to actually find these critical values. So let's say we want to find the t value such that the area under the distribution to the right of t is 0.2, and we're going to assume 10 degrees of freedom. So what we're going to do is, if you think about it, we have 0 in the middle. We're finding the we're finding the critical value, t 0.2, such that the area is 0.2 or 20% to the right. So what we do, and I'm going to pull up another thing here. Let me find it. Yes, here is my tables, okay, and I'm going to scroll down a little bit. I would like my t-distribution, okay, so it's right after normal distribution and then t. It's table 6. And what I'm going to do is I'm going to find 10 degrees of freedom, and I'm going to find 0.2. So I have 0.2, 10 degrees of freedom, and you'll see degrees of freedom are on the left, 0.2, it's right here, so I get 0.879 as my critical value. And they have 0.8791, so this is slightly more exact, but this would be how you would look it up on the actual table. Oops, sorry about that. Okay, so the reason that we need to know those critical values is because they are used in the creation of the confidence interval. So if you remember, we had critical values from the previous section as well. We had z alpha over 2, and this was found typically just using it's one of those 3 values for the 90%, the 95, and the 99. We had those 3 kind of common values, the 1.645, the 1.96, and so on. Here, though, your distribution depends on sample size, which corresponds with degrees of freedom. So we have different critical values even if we have the same level of confidence. So we have to do a little bit more work in order to create our confidence intervals by hand because we have to go in and we have to find a critical value each time. So a couple of things have to be true. Our sample data has to come from a simple random sample or a randomized experiment. Sample size needs to still be relatively small. And then one of two things has to be true, which we talked about in the previous chapter, which is either that the data has to come from a population that is already normally distributed, or we have to have a large enough sample size, which we're going to say approximately 30 or larger is fine. So in order to construct the confidence interval, this looks very similar to the other formula that we had in the previous section, but basically we take our point estimate, which in this case is x bar, and then we add and subtract, depending on if we're doing our upper or lower bound. And we take our critical value, multiplied by s over the square root of n. S is your sample standard deviation, n is your sample size. Degrees of freedom, we talked about, I think back in chapter 3, it's been a while. But basically, degrees of freedom is always one less than your sample size, because up until that last observation, the data has some freedom to be where it wants, but because of the fact that errors need to be kind of centered, and you don't have to worry about this too much, but because of this, that last observation is kind of forced to be a certain value. So we call the number of degrees of freedom n minus 1. Now I think the way that I described this before was a little more maybe not as applicable to the stats part of it, but makes a little more sense. And that's if you think about like a classroom of people, and let's say we have 30 students and I have 30 pieces of candy, okay? So I go to the first person and I let them pick what candy they want. And I go to the second person, let them pick a piece of candy. All of those people have freedom to pick the candy that they want, except for that very last person. The very last person, since I only have 30 pieces of candy, just gets whatever piece of candy is left. They have absolutely no freedom. It's the same idea here. Up until the 29th person, we have 29 degrees of freedom, so basically 29 people have freedom. That one last person just kind of gets stuck with whatever. So let's look at an example. Let's calculate this by hand, and then again, I'm going to show you guys how to do it in StatCrunch. So let's construct a 99% confidence interval for our pennies. Okay, so we have our 17 pennies again. And one thing we want to check is to make sure that it looks normally distributed. And so here is a normal probability plot. This was created using Minitab, I believe, but you can create this using StatCrunch as well. That's back from chapter 4. But this looks pretty good. So the first thing I want to walk through is finding the critical value, because critical values, again, when we're dealing with population mean, or estimating the population mean, can be a little tricky because we're using our new distribution, our t distribution. So we know we have 17 observations, so the degrees of freedom are going to be 16. So again, think about our people with candy. If we have 17 students, 16 of them have freedom to choose the candy that they want. Now alpha in this case is 0.01. If we go back a couple of slides, you'll see we wanted a 99% confidence interval. So that would correspond with a 1% kind of not confident. So if you kind of pay attention to the way that these formulas are written, if I go back to my formula here, you'll see that the critical value is written as T alpha over 2. So if you think about the fact that we have tails, we have left-hand tails and right-hand tails, what we need to do is take our error, our alpha over 2, or our alpha, sorry, and we need to divide it in 2. So we take our 0.01 and we divide it in 2 and we get 0.005. So in order to find the critical value, I just need to go to my table, and I'm going to just pop open this table again. I have 16 degrees of freedom, so I'm going to go down here to 16, and I wanted 0.005, so if I work my way over, 0.005 is up here, 16 is down here, so my critical value is 2.921. So that is going to be my critical value that I have right here. And then I'm going to use this in the creation of my confidence interval. So now in order to create my confidence interval, I take my x bar, which was my sample mean of my penny weight, so 2.464 grams, and I add and subtract my critical value, which was 2.921 from the previous slide. And that critical value needs to be multiplied by S, which is my sample standard deviation. That would just be 0.02, and this would just be calculated. We had those 17 observations. You would use stats, summary stats, and you'd get the mean and the sample standard deviation. Sample standard deviation in this case is just 0.02, and you divide that by the square root of n, so square root of 17. And again, you might want to pause it at this point, try to plug this into your calculator, make sure you're able to get values of 2.450 and 2.478. So once we have that, we would write a little interpretation, and we could say that we are 99% confident that the mean weight of pennies minted after 1982 is somewhere between 2.45 and 2.478 grams. Now, if we want to use StatCrunch, we can do this a pretty simple way here. So let me scoot this over a little bit so we can see both of our problems. So let me close out of that. I have all of my penny weights typed in here, and you'll notice this data was not already summarized. So what I'm going to do is when I go into stats, I'm going to do t-stats. I have just one sample. And before, if you remember, I chose with summary because I already had summarized data. This one, I actually have the raw data, so I'm going to do with data. I select my penny weights, and I want a confidence interval. I wanted 99% confidence, and then I click compute. And it gives me a lower limit of 2.45 and an upper limit of 2.48. Now, these are going to be slightly different values than if I go back a slide. They round to the same hundredth place, but not the same thousandths place. That's just because StatCrunch has the ability to be a little more exact than we do when we're doing things by hand. So the last concept in this section is determining sample size. So again, we can find sample size if we are interested in doing so in order to obtain a certain margin of error, a certain level of confidence. And we can do this for a mean. Now, what you'll notice, and this is kind of an interesting point, is that we have z in our formula. Now, if you remember from a couple of slides back when we were calculating our confidence intervals, we had t in our confidence interval. So if you think about it for a minute, the t distribution requires us to actually know the sample size, because if you go to your t distribution table, one of the two things that you need to look up, first thing is the alpha over 2. The other thing that you need to look up is degrees of freedom. Degrees of freedom depends on the sample size. So if we're trying to calculate sample size, we cannot possibly know what the degrees of freedom are. So what we have to do is we have to use the normal distribution in order to do this sample size calculation. And again, when we use this formula, we always have to round up to the nearest whole number. So let's look at an example here. Let's go back to our pennies, and we want to know how many samples would be required, or how large of a sample would need to be required to estimate the average penny weight within 0.005 grams, 99% confidence. And we're assuming that S equals 0.02. So Z alpha over 2, we know that alpha is going to be 0.01, 1%, okay? And we know that 99% confidence back from section 9.1 corresponds directly with a critical value of 2.575. That was kind of one of our nice critical values on our table, so we're going to use that. So in order to calculate our sample size, we take that critical value, we multiply by S, which is 0.02, we divide by our error, which was 0.005, and then we square the whole thing. And we end up with 106.09. That would round up to 107. Now I want to show you kind of quickly how to do this in StatCrunch as well. And it works pretty nicely. So if we go again back to StatCrunch, stat, this time I have, if you look, I'm doing t-stats, okay? And, or sorry, oh, I typed the wrong thing here. Oh no, I didn't. T-stats, one sample, power sample size. And we want that confidence interval width. again. So this one is t-stats, one sample, power / sample size. Now this one, the confidence level is 99%, standard deviation 0.02, and the width that we want, again, is going to be twice whatever my error is that I'm willing to deal with. So it's going to be 0.01. And if I do compute, I get 110, very close to the 107. Again, our answers aren't going to match exactly because of the fact that StatCrunch has the ability to do more exact calculations. Okay, last thing I want to look at is just this slide here, which is included in your lecture notes as well, and it's also in the textbook. And this just sort of puts everything together because we created several different confidence intervals, solved a few different types of problems, and it just can get confusing about what assumptions have to be met, what should we be checking, that kind of thing. So this is a nice little flowchart that sort of just walks you through how to estimate different parameters. So if you're estimating a population proportion, n times p hat times 1 minus p hat has to at least be 10. And if that's the case, then you just construct an interval around p using normal distribution. So that was from 9.1. Now, if you're estimating mu, your population mean, if sigma is known, that's not something that's typically going to happen, but if sigma was known, then you could calculate a z interval. This green part down here, we're not going to be doing this in this class because there aren't going to be any questions where we actually know sigma. This green part over here, we're also not doing. We're not creating confidence intervals for our standard deviation. We could though. Now, since sigma is not known in our case, what we have to ask ourselves is if our sample size is large enough. So if n is greater than or equal to 30, meaning we have a large enough sample size, then we can compute our t interval, which works just fine. Now, if n is not greater than or equal to 30, then if the data comes from a population that is normally distributed and it doesn't have outliers, then you can still compute the t interval, which works just fine. But if that's not the case, so if standard deviation is not known, if your sample size is not 30 and your data did not come from a normal distribution, then what you would have to rely on are some things called non-parametric methods. Those are outside of the scope of this class, so we're not going to be covering them. But that's just kind of one sort of thing to note, is that we can still do things if all of our assumptions are met. We're just not going to be dealing with this in this particular class. So that's it for this week. Good luck creating confidence intervals, and please let me know if you have any questions.